I want to do now is I want to talk about section 1.5. What I'm going to do at the start of section 1.5 is just kind of give you the lowdown and motivation for what we're going to be talking about. The nitty-gritty really comes in with pushing buttons on your calculator and doing all of that fun stuff. Okay? But I want to give you an idea as to what we're doing and why we're doing it. So, what I'm going to do here is the following. I'm going to draw two different data sets. And if you don't want to write this down, that's fine. Doesn't really matter. But this is section 1.5, and it's called your least squares line. I'll explain all of it. Okay? So, but first let's make the overhead accessible. Alrighty. Now, very often, and you guys are in majors that use this in an applied situation, okay? You're given a whole bunch of data, and you want to make sense of the data, okay? And so a lot of times what's going to happen is you're going to have a lot of data, and you want to find a function that best approximates the data. Why? Well, because suppose you're looking at, for example, the number of people who do, who have a cell phone. Okay, you might want to say, okay, based on the growth of the cell phone use over this period of time, why don't we start predicting future trends? Okay. Well, it turns out that you can have a set of data that looks like this, okay? Or you can have a set of data that's a little nicer looking. Now, it turns out that when you deal with a set of data, sometimes you can approximate it by a line, sometimes you might use a parabola or an exponential function or what have you. In this class, the only function we're talking about are lines. So we're only going to approximate these things with lines, okay? Don't worry about anything else. Now, next thing. Given any set of data, you can find an equation of a line that best fits the data. The thing is, it might not fit it very well at all. You can still find a line, okay? So if you agree this doesn't really look much like a linear function, but you can still find a line that best approximates the data, okay? Your calculator is who is going to do these computations for you, okay? Whereas here, don't you agree that that's pretty linearly related, okay? This line at least gives us a better approximation of the data than when stuff is all over the place. So, one of the other things we're going to want to know is not only what the equation of the line is, but how well it fits the data. Because you see, if the line doesn't fit the data well, are you going to want to use it to make any future predictions? Heck no, right? But if it is a good fit, then you're like, woo, score. Okay? You're going to want to use that for future predictions. So, those are the things that we're going to be dealing with. Now, our calculator is going to be doing these computations for us. I will tell you, it would be good for you to look in section 1.5 at the formulas that are actually used to find the equation of the line, just to make you appreciate your calculator that much more. Okay? I mean, it's doable, but it's kind of a wreck. So, now, the next thing is, okay, our goal here is number one, to find the equation of the line and also to determine if it's a good fit. Let me first tell you why this is called your least squares line, okay? The way the line is found is the following, okay? And again, you don't have to write this down, I'm just motivating the name, okay? Well, what we want to do is the following. You look at the distance, the vertical distance between each data point and the line that best fits the data, okay? Now, do you agree if I take, for any point above my line, my data point minus the point on the line, get a positive number. Whereas for the data points below, if I take the data point minus the value on the line, I'm going to get a negative number. Okay? Remember, these things offset each other. So the way we get rid of negatives is we square things. So essentially, what's going on here is we're looking at the vertical distance between each data point and the line. We're squaring those distances so that they're positive. That's where the squares comes in. And don't we want these distances to be as small as possible when we add them up? Because if they're as small as possible, that means the line is closer to your data. So that's where the name least squares line comes from. Does that make sense? Okay, so really you're just looking at these distances, and you want the distances between your line and the data points to be as small as possible. That means it's a better fit. Okay? Now, one question you might ask is, how do you know if your line is good or not? Your calculator is also going to tell you that. Okay? So, how good of a fit is the line? Well, the thing that determines that is called your correlation coefficient. On your calculator, it's denoted by the letter R. You'll see it soon enough, but let me first talk about this. All right. Do you guys agree that if your line, as you go from left to right, goes up, you have a positive slope? And if, as you move from left to right, your line goes down, you have a negative slope? Well, R follows the same sign as the slope of your line. Okay? So let me say this. If your slope is positive, R will always lie between 0 and 1. 1 means it's a perfect fit. It almost never happens unless it's a textbook question. Okay? Now, how do you know how good of a fit it is? Well, it turns out we have this essentially standard operating procedure. If R is between 0 and 0.5, don't use it. It's not good. If R lies between 0.5 and 0.8, we say it has a moderate fit. And if it lies between 0.8 and 1, it's really great. In other words, the closer it is to 1, the better of a fit it is. Okay? In a similar manner, if your slope is negative, then R is going to be negative. Then R lies between 0 and negative 1. And again, in a similar manner, if R is between 0 and negative 0.5, again, don't use it. If R is between negative 0.5 and negative 0.8, again, that's viewed as a moderate fit. And if it's between negative 0.8 and negative 1, it's really great and terrific. Okay? Any questions this far? All right, so what I want to do is go through a couple of examples with you, teach you how to put these in your calculator, and then once we find these lines, we're going to just play around with some computations, because there's no point in finding an equation of line unless we get to play. Okay? So, if you guys want to go get out your calculators, that would be sweet. And again, if you don't have your calculator, just write down the steps. Now, the first thing that I'm going to do here, you guys, is something that you should only have to do once. Okay? What we have to do is essentially turn on our diagnostics so that we get our R value. Okay? If for some reason when you're taking an exam, your R value doesn't show up, all you have to do is raise your hand and I'll come over and turn it on for you. Okay? But let me show you how to turn it on, just because. Then you know too. Okay? So, if you look at your calculator, again, this is just a one-time deal probably, but it's kind of an interesting deal anyhow. See your number 0? And do you see how above the 0 it says catalog? If you have a different kind of calculator, find wherever it says catalog. Okay? You want to get to the catalog. So I'm going to hit second 0. Now the catalog is actually fascinating. Okay? Why? Because it is an alphabetical list of absolutely everything your calculator can do. Isn't that neat? I think it is. Okay? Those of us who grew up way before computers and all of that stuff, trust me, we appreciate these. So, ready? We want to turn on our diagnostics. So I'm just going to cruise down my list until I get to my D's. See how it says diagnostic off and then diagnostic on? You want to get to diagnostic on. Hit enter, and then hit enter again. Okay? You shouldn't have to do that again, but calculators can tweak sometimes, so that's why I said I'll turn it on. Everyone with me that far? Okay, so what I'm going to do is take one example out of your textbook. You'll always be given a table. So the first example I'm going to look at, and if you don't have your book, don't worry, I'll write all the relevant information down, is I'm going to do number 12 in your book, and this is called e-book audience. It says the number of adults in millions using e-book devices is expected to climb in the years ahead. That makes sense, doesn't it? At least until new technology comes out. All right, it says the projected number of e-book readers in the U.S. from 2011 through 2015 is given in the following table. Okay, you need your table. So year and number. So we got 2011, 2012, 2013. Wow, this is a big table. 2014 and 2015. And remember, these numbers are in millions. That just helps us interpret everything in the end. And so these are given. So 25.3, 33.4, 39.5, 50, and 59.6. All right, so this is saying, for example, in the year 2014, there were 50 million e-book readers in the U.S. You guys all with me here? Okay? Now, I'm going to change this slightly from actually not on this one. What I'm going to say is let's let x equals 0 correspond to the year 2011. And the first things that we want to do are find the equation of the least squares line and our correlation coefficient. All right. So it's really important to take note when they want you to let x equals 0 correspond to a year as opposed to entering the actual year. So do you agree if I let x equals 0 correspond to the year 2011, then 2012 x is going to be 1, 2013 x is going to be 2, then 3, then 4. Okay? Sometimes we enter the actual year and sometimes we do it this way. I will always specify how I want it done. You guys with me this far? Okay, now, what we need to do is enter these as lists in our calculator. So I want you to look at your calculator, and I promise you this hard, but I want to go through all the steps very detailed so we're all together. Okay. Well, here we go. This is doing some kind of statistics. So we look at our calculator, and do you see how there's a button that says Stat? It's right next to my up, down, left, right arrows. Okay? Hit that button. So I'm going to scroll up for a moment here. Number one, you hit Stat. Now, first thing you're always going to want to do is edit, because you see we need to enter these lists. Now, I'm going to hit edit, and look, I've got stuff in my lists, okay? Because I've done this before. You may or may not have anything in your list, but after this first example, you will. So what I want to do is I want to clear my lists. The easiest way to clear your lists is you want to go up to L1. Watch what I do. I'm going to use my arrows. This is so cool. So over and up, see how it's on L1? Okay? In order to clear that list, what I then do is I hit clear, enter. And then we're going to do the same thing for L2. Watch. So I'm going to hit clear, enter. All gone. And then I'm going to go over to L2. Go up to it and hit clear, enter. You guys with me this far? All right. Now, our next step is to actually enter our lists. You guys always, your X values will be in L1 and your Y values will be in L2. So, in my L1, do you agree I just need to enter 0, 1, 2, 3, and 4? So what I do is I hit 0, enter. 1, enter. 2, 3, and 4. You guys with me this far? All right. Now what we need to do is go over to L2 and enter our corresponding function values. So when X was 0, didn't we have 25.3? So you put 25.3, enter. And then do 33.4. And go on down the list. Now, I understand that it's really easy to make typos on these sorts of things. So one of my guarantees is number one, if you make a typo, yeah, you're going to get the wrong equation of the line, but I never make that work very much because typos are easy to make. And that's also why I tend to make my tables small. Is everyone okay this far? Yes. It should be 50. Thank you. I would have gotten the wrong line. Well, I'm speaking of typos. All right. Y'all with me here? Cool. All right. This is something probably most people know on their calculator. How to quit. Right? You hit second mode. Get out of there. Okay. Next. The way we do these computations is, again, hit Stat. It's really only one button you need to remember. I think we want to do a calculation. So what I'm going to do is I'm going to go over to Calc. Hit your arrow to go over. All right, the one that we're interested in is the lin ray. That's a linear regression. You see, you could do a quadratic, a cubic, a quartic. We're not going to go there. We're only dealing with the lines. Okay? Now, my calculator here says AX plus B. Do you guys agree then whatever value I get for A is my slope and whatever value I get for B is my y-intercept? Some people's calculator says BX plus A. You just need to take note on that because then your B is your slope and your A is your y-intercept. way it goes, you're going to go down to that 4 and hit enter. So, what we found is the following. The equation of my line is 8.52x plus 24.52. We do not use the r squared in this class. If anyone's going on to take stats, then you will use the r squared. Yes? Okay, if yours says list, keep hitting enter. And then you'll get it. All right, my r value here is 0.996. So, tell me something. Is this a good line, a moderate line, or scrap it? It is really great line. It's not the best, I'd say. You with me here? Okay. Are there any questions this far? All right. Now, a couple things I want to point out. Notice my y-intercept. In other words, initially, when we started looking at this, we claimed that there were 24.52 million readers. Notice that is slightly different than what our data point was. It was 25.3. But that's actually not surprising because, again, this is the line that best fits all of your data. Okay, so it's not going to fall exactly to it. All right, you guys with me this far? Now, I want to do 3 computations with this line, and then we're going to do another practice. Okay? Because there's no point in computing a line unless we get to play with it. So, my first computation that I would like us to do is the following. What if I want to know, I want to find the number of ebook readers in the year, how about 2020? Okay, now we're going to use this line. Now, suppose on your test you made a typo, say you got the wrong equation. Yeah, you're going to lose like a point, okay? But if you use your line correctly for all your computations, you're not going to lose any more points. We're going to grade everything based on the line that you found. So if you don't know how to find the least squares line on the test, make one up so at least you can go through the rest of the problem. Okay? So, we want to find the number of ebook readers in the year 2020. Well, am I wanting to find my x value or my y value? I'm wanting to find my y value because I'm wanting to find the number of ebook readers. Therefore, I better be given my x value. Am I directly given my x value? No. Okay? It's really close though. Do you remember that 2011 corresponded to x equals 0? So, what x value will I use for 2020? 9. Right? It's 9 years later. So, I can compute this then. 8.52 times 9 plus 24.52. You guys with me? And in case anyone really cares, we're going to have 101.2 million ebook readers. Does that make sense? All right. What if, on the other hand, I want to ask you, in what year will there be 200 million ebook readers? Now, going out this far, it's kind of nonsensical, you guys. I mean, because we're probably, we're already at like almost 2/3 of the U.S. population here. Okay? So, do you agree now I'm looking for my x value because I'm given my y value? You with me there? Can I solve this? Absolutely. What is our first step, you guys? You subtract 24.52 from both sides. I'm going through the algebra because I know for some of you guys it's a sticky point. All right. Last but not least, how do we get x all by as lonesome? You divide both sides by 8.52. And if we do that, we get 20.6. So what we would get then is x is about 20.6. I always tell you to round to the nearest year. You guys, am I done?
Sure.
No. This is saying in the year 21. Okay? We actually now have to convert it to actually what year it is. Again, remember x equals 0 corresponds to the year 2011. So x equaling 21 corresponds to what year? 2032. Right? Just add 21 on here. Guys with me? All right. One last thing I want to do in this line is the following. I want us to be able to interpret our slope. Okay? You guys agree that your y-intercept is just your initial value. Okay? It's the value when you started looking at this sort of thing. But what does the slope of 8.52 mean? Okay? So, let's interpret the slope. Okay? Well, remember when we look at our slopes, we're looking at a rate of change. Do you all agree that when you look at the slope of a line, you're essentially saying for every increase in your